Swayam Prabha. Digital India. Educated India.
Okay, so in yesterday's class we started looking at absorptivity. Absorptivity is a key radiative surface property because in the design of solar collectors and so on we want high absorptivity in the solar part of the spectrum, that is the visible part of the spectrum, and if you want a body's temperature to go up so that you can extract the heat, it should have low emissivity in the infrared part of the spectrum. Okay, so we defined the basic quantity of interest as far as absorptivity is concerned, that is the spectral directional absorptivity, and then we looked at the Kirchoff's law which gave a relationship between the spectral directional absorptivity and the spectral directional emissivity, but I think some people were not very convinced and some lingering doubts were there. What is this Kirchoff's law? Suddenly I did something and I proved it and it was not clear. So the first few minutes we will go through the derivation again, and it is also 8 o'clock in the morning, so people are fresh. We will understand this and then we will go to the other definitions of absorptivity, and then to reinforce whatever we have learnt we will work out problems. Okay. So the configuration for proving the Kirchoff's law is like this. Before that I want to tell you that the Kirchoff's law is an experiment, is an accepted law of nature because it can be experimentally verified. Whenever you do experiments, if you have the equipment to measure epsilon lambda dash and if you have the equipment to measure alpha lambda dash, it is found that it is always true. Now we are trying to do some theoretical explanation so that our understanding will improve. Okay, whether we prove it right or not, experimentally whenever you do it is always true, just like the second law of thermodynamics. If you are not able to prove, that is the inability of intellect, but the second law of thermodynamics is an inherent law of nature. Okay, so the nature does not care whether you know how to prove it or not, it will behave according to its wish. Okay, so this we are trying to rationalize and internalize what is going on. Do we have an explanation of this Kirchoff's law? That is why we are trying to do this. So we come up with complicated thought experiment, somebody kept in a large enclosure, there is vacuum and it is initially at different temperature, and we do all this so that with our present level of understanding are we able to explain, are we able to understand this better, are we able to crystallize our thoughts on this or understanding on this better, that is the goal. Now let us take a hollow enclosure, the enclosure wall, I will speak a little slow, so this is a key concept. Okay, so let us consider a hollow enclosure, the enclosure wall is at T, this can be maintained at T by several ways. I can send cold water at the same temperature. Okay, whatever heat is emitted by any body in the center can be taken care because this body is so big and whatever body we are keeping in the center is very small. Or I can allow steam to condense, I can have a constant temperature bath and all that, so I can maintain the temperature at some T. Okay, this T can be 30 degrees, 300 degrees, whatever Celsius. Now there is vacuum inside and there is a small body which is kept inside. So do not ask me how this small body was kept inside. So you have to make a hole, isn't it? How do you do this? Okay, you make some hole, you put it and then close it and assume that, or if you are able to come out with some special machining this thing, I mean if you start asking questions then sometimes it will lead to madness, but assuming that it is possible for us to keep something and still there is vacuum. Now this fellow is a body which is not a black body, it is a body which is not a black body, it has got an epsilon lambda dash. Epsilon lambda dash will be a function of lambda T theta phi because this is a general, this is the spectral directional emissivity. Up to this it is clear, so it is not a black body. Now initially this fellow was heated, Tw is greater than T infinity. Now we allow it to cool. After sufficiently a long interval of time has elapsed, this fellow will also come to T. Okay, because of the transfer of heat, this temperature will not change because this is a small body in a large enclosure, this is capable of withstanding any amount of radiation which is coming onto it, that is like our sink, the ambient. Okay. Now up to this the story is clear. Now I want to make some interventions. What I am saying is, I am at liberty to put some filters. Okay, these filters could be cellophane sheet, transparent sheets, or glass sheets, or okay, perspex sheet, whatever. And each of these sheets allows radiation to pass through only in a wavelength interval d lambda about lambda. And assuming that I have enough knowledge of engineering, it is possible for me to come out with a band pass filter which can permit radiation in any d lambda about lambda getting, regardless of whether it is visible, infrared, ultraviolet, and so on. Now the beauty of this is, if it is allowing only in a wavelength interval d lambda about lambda, this body is permitted to emit radiation only in this wavelength interval d lambda about lambda, because any other radiation which is any radiation emitted by this body which is outside this d lambda will be reflected by this fellow and it will come back again to this fellow. Okay. So radiation only in the wavelength interval d lambda about lambda can escape and hit the surroundings, and this is inevitable because the body is at a temperature greater than 0, T is not 0 Kelvin, so it will continue to emit. At the same time the body is also in equilibrium with the surroundings, therefore it must absorb the same amount of radiation. Okay, upon equilibrium whatever is emitted must be equal to whatever is absorbed. Okay, therefore if you apply the first law of thermodynamics for this body which is in equilibrium with the surroundings, the following thing holds. So upon reaching equilibrium the following thing holds. What is the following thing, what holds? This is exactly the same as what we discussed in yesterday's class. Q net is equal to what is going minus what is coming. Okay, so what is Q net? For this body what is Q net upon reaching equilibrium? Q net, because if Q net is non-zero, its temperature has to decrease or increase with time. Therefore emitted plus reflected minus incident equal to, what is incident minus reflected if there is no transmission? Therefore this you can put within brackets, that is to help your understanding, that is all. Okay. If some people got a doubt yesterday how suddenly I said emitted is equal to absorbed, that is the explanation. Okay. Now if this equation, are we putting equation 1, is there a number for this or? Did we use numbers yesterday? 1, okay. Now we will have to write expressions for absorbed and emitted. What about absorbed? Now apart from deciding that it will be only in a wavelength interval d lambda about lambda, I can also decide about the direction. I will cut out the radiation emitted in other directions, I can allow the band pass filter to allow the radiation in one direction only, all that I can control into Now I will use only T for this. Now epsilon lambda dash, I should not put I lambda I, epsilon lambda dash multiplied by IB lambda, correct? IB lambda corresponding to what, which temperature? T, very good. I do not have to put theta and phi because IB lambda is independent of theta and phi, okay, but cos theta other things will come. Okay. But what is the beauty now? What is I lambda I itself? A spherical cavity with vacuum inside is equivalent to a whole drum, is equal to a black body. Therefore, the incident radiation as far as the small object is concerned is basically coming from the walls of the enclosure. The walls of the enclosure, there is perfect reflection among its various surfaces, right? That is what you have seen. So from here it will go like this, here it will go like it will go. And since this is also at the same temperature as this, I lambda I corresponds to uniform and isotropic radiation from the walls of the enclosure, which can be deemed to be a radiation from a black body at a temperature T, which is the same as the temperature of the small body within the enclosure. Therefore, I am allowed to change I lambda I to IB lambda. Is that clear? Maybe this was missing in yesterday's, I went too fast, so I did not make it clear probably yesterday. Now it is clear. So there are some small manipulations I am doing, but it is clear, the argument is perfect. So I lambda I is actually IB lambda, because therefore I can now cancel. Therefore, or we can ditch this now. So this is the Kirchoff's law, correct? Is this clear now? Always true. And it holds good without any constraints. As I told you yesterday, if somebody asks you a question, what is Kirchoff's law, you should not say emissivity is equal to absorptivity, that is not correct. That is a highly processed, simplified version of the Kirchoff's law for a gray diffuse surface, right. So now you can complete the exercise by saying, if some people do not want to cancel here, you can put this as equation number 3, put this as equation number 4, if you feel that will make you understand better, right. For a gray diffuse surface, epsilon of t, right? Epsilon of t is equal to alpha of t, right? Did you write like this? Okay. The next property we saw yesterday was hemispherical spectral absorptivity, right? For the sake of completeness, I will quickly go through this. We have already seen this yesterday. Since I started with Kirchoff's law, I think it is logical for me to do this. What is the goal of defining this quantity? What is the symbol for this? Alpha? Okay. So what is the goal of introducing and defining a quantity like this? Basically, I have an elemental surface which is having an area dA, okay. From the this is not correct. So this is a unit vector, huh? So there is an elemental surface dA. I am considering the hemispherical space above the dA. Now radiation from the hemispherical space is coming onto this object and falling on this object. So it is coming like this. What is the total radiation which is coming from the hemispherical space which is falling on this object in a particular wavelength interval, okay, divided by, no, that is the denominator. What is the fraction? What is the fraction of the total radiation from the hemispherical space above it in the hemispherical solid angle at a particular wavelength interval which is absorbed by the body? Rather, from the hemispherical space, what is absorbed divided by whatever is incident. Okay, so that is the goal of defining this, and we always assume that once you go to quantities which are integrated versions of the primary quantity of interest, I assume that alpha lambda dash is known. So given the information of alpha lambda dash, how do you calculate alpha lambda, alpha dash, and finally alpha? That is the logical, that is the way the story progresses. Okay. Now if you want to write a mathematical expression for this, what should be alpha lambda? dq absorbed, correct, should be a function of lambda and should be a function of the temperature of the absorbing surface. Theta I phi a are removed because we are integrating over the hemisphere, divided by and I can use the notation phi I to I subscript denotes the incident direction. Can you fill up the denominator? I lambda I, the incident radiation could be a function of lambda, it could be a function of direction. I do not have to write the temperature if I know what this I lambda I is. Only in the case of incident radiation from sun I need to write the temperature, because if I know the temperature of the sun I can assume it to be a black body. Otherwise I know that somebody will give me I lambda, somebody will give me how I lambda varies. Is that clear? Multiplied by cos theta I multiplied by dA, because I want the numerator to be in watts. It okay? Correct, very good. Lambda? No, that is correct, not correct. Yeah. Phi I, na? Then is it in watts or? Huh? It should be watts per micrometer then. What is the denominator? Watts per meter square per micrometer steradian. Okay. No, I can multiply whatever. So, I don't want to confuse you further. Now, what are the units you tell me? Yeah, we will write. This also no problem. Even if you multiply by d lambda numerator denominator, I have no problem because d lambda can be pulled out of the integral, d lambda can get cancelled. Okay. We should not get into such type of this thing, difficulties. Alright. Now dA is also outside the integral. So it depends on, I am at liberty to define dq. I can call it dq dash d dash whatever. Okay. Now I should write an expression for, now what is this? 3, 4, no, yesterday we did a lot of things, no, 4, 5, 6, 7 have we written? This was 7? Okay, then we will keep it as 7. So we will call this as 8. Now tell me dq absorb. Now this will be alpha lambda dash. Okay. Yeah, sure. Alpha lambda dash into I lambda I. Yeah, put that bracket. What do you want to call this? Equation 9. So what is exactly the departure from what I taught you yesterday? Yesterday I gave you the final answer, now I am writing the intermediate step. What is the basic definition of alpha lambda? Numerator by denominator. Denominator everybody knows. Numerator I wrote it as equation 9. Then I am substituting for the numerator in equation 8. So from 8 and 9, once I show it for hemispherical spectral, the other two quantities I will directly give you, I won't do this detailed derivation. Is it okay? Now, so alpha lambda yeah, you please put all those brackets in, huh? I can get rid of the dA. Is it okay? You are not allowed to leave out what is there in the brackets. For I lambda I and alpha lambda you do that, fine. So this is now what is the next? Absorptivity, huh? Yeah, total but directional total, correct? So what should be the symbol for this? alpha dash. The lambda dependence goes because we are integrating with respect to lambda. Correct? Okay. So, equal to d theta d phi is there. Is it there? Only d lambda, correct. Because Rajesh, you are not happy with that. If you are not happy with that, you write cos theta sin theta d theta, I have no problem. Cos theta sin theta d theta d phi will come both in the numerator and denominator. Integration is with only respect to only lambda, you can pull it out. So, no confusion, there is no hanky panky, everything is clear. Okay, we are proceeding from the basic steps. Okay, divided by now I think you must have got a good idea of how to proceed from spectral directional to all this, regardless of whether it is emissivity or absorptivity. The next week's class, when we are doing reflectivity, I hope all of you will do it very fast. So that will be the third property we are discussing, correct? Into, okay, let us keep this d omega. Okay, so some people are frowning. So now anyway the integration is only with respect to this, so I can ditch this d omega. I can remove the cos theta I also. That cos theta I comes because of I lambda I cos theta, right? Okay, because I is based on the projected area, cos theta will always come. Because the radiation, the incoming radiation, all the incoming radiation will not be normal to this dA, correct? Only when the zenith angle is 0, that will be cos 1, no, cos 0 which is equal to 1, alright, fine. Now the last one. So it is sans lambda and dash, that is it is without lambda and dash, it is just alpha, and I expect it to be a temperature of the absorbing surface, so I retain the TA, just like we wrote emissivity is a function of temperature. Okay, so alpha TA I always leave that I lambda I, right? Some of you wouldn't have waited for me, you would have wrote it yourself, correct? No, that is a very important result, because from alpha lambda dash, how you do this 3 integration, that is 2 integration with respect to 2 angles and 1 integration with respect to lambda, and finally get the, okay. So what will be this 11 and this 12. To cut a long story short, if alpha lambda dash is given to us, we have a mechanism to calculate alpha. If the distribution is known, you can integrate it analytically or you can integrate it numerically and you can get it. And this alpha is of final engineering interest to us, because we are with alpha and emissivity, we will work with a we will start working on the actual heat transfer problem, which could involve modes other than radiative heat transfer also. Okay. So once you have got epsilon and alpha, you cross 2 important hurdles. What is the fundamental nature of radiation? What are the laws governing this, sigma t to the power of 4 and all that? If it is not a black body, how to characterize that? You have crossed. The next 2 hurdles will be, how do you take care of the geometric orientation of the various objects, and then if so many objects are acting together, how do you take care of the overall formulation? What is the influence of one object on the other? Okay. Now what will happen to equation 12 if the irradiation is from a black body at a temperature Ts, that is T of sun? Let us look at a special case. If you consider a special case of irradiation from a black body at a temperature Ts, the denominator will become sigma Ts to the power of 4. Then alpha is no longer independent of the temperature of the surface from which the radiation is originating, because the Ts to the power of 4 is there in the denominator of this expression. Therefore alpha becomes a function of Ta and Ts. This is valid even if the irradiation is from a diffuse object, a diffuse grey body at a temperature Ts. Are you getting the point? Okay. Now we will write that and close the discussion and start solving problems. For the special case, yeah, you fill up all the other things. The most significant, the most profound and subtle change I have made on the left hand side of equation 13 is what? The subtlest but yet profound change I made on the left hand side is I made alpha a function of Ts. Okay. Yeah. Now I think we have got a good handle on 2 basic properties. We should start solving problems. Okay. Problem number, is this clear up to this stage? Okay. Now if you start solving problems, it should get very interesting. Problem number 11. Please take down this figure. Shall we make this 0? Okay. This alpha lambda versus lambda. Alpha lambda is lambda for a opaque surface, for an opaque surface. It is going like this. Okay. From this, can you calculate alpha? What are the information do you need? Right, without irradiation, or I should tell you at least this is from black body, or I should give you I lambda I, otherwise you cannot do anything. If I give you emissivity, if I tell you the temperature, you can do the F function chart and you can calculate. Therefore, if alpha lambda versus lambda is given, that is not enough. I should give you the nature of the incident radiation, or I should tell you from where it is coming, correct? So, I will give you the distribution. Let us make this 1.5. So, this I lambda I watts per meter square micrometer, okay. So, tell me a good number for this. 10 per I lambda I is so high, man. 40,000. I will make 8,000, 6,000, 40,000 may be too much. I have no problem. Okay, somebody wants 40,000. Well, we will take 40,000. Let's see what happens. Okay. So, if you don't get the right answer, you catch hold of Vikram. He suggested this 40,000. Okay. Now take down the problem. The spectral hemispherical absorptivity of an opaque surface. The spectral hemispherical absorptivity of an opaque surface and the spectral hemispherical absorptivity of an opaque surface and the spectral distribution of incident radiation are given in the figure. A. What is the hemispherical total absorptivity of this surface? A. What is the hemispherical total absorptivity of this surface? Two. If this surface is diffuse, I gave A or 1, A, then sorry B, if this surface is diffuse, and is at 1000 Kelvin, so what is the question? What should be the question?
What is the amount of radiation emitted?
Find the no, before that
Emissivity.
What is its total hemispherical emissivity? Okay, if the surface is diffuse and is at 1000 Kelvin, what is its hemispherical total emissivity? Part B. Part C? Yeah, please tell me what should be part C. What is the net radiation heat transfer from the surface? That is outgoing minus incoming. C is what is the net radiation heat transfer from the surface. First thing is I will calculate the denominator, right? Fine. So, alpha Is it okay? This is always there, man. Correct? There will be still one or two people who are always worrying, sir, what happened to the sin theta, cos theta, d theta. So for those doubting Thomases, I will you can write the numerator denominator and cut it out if you want to be clinically correct. Okay. Now denominator is very easy for us to calculate. Vikram, what is the answer? Huh? Area under the curve 1.5 into 40,000 plus 80,000 plus, I did not give you this value. What did you take it as? You just took it, huh? Okay, we will take it as 5, that is good. 0. So it is again same 30,000, huh? What is this 140? $140,000, correct? Vikram, I don't even know how we are given 1000 Kelvin, I don't know how it is going to come up. Huh? Let us see. Now alpha equal to, what about the numerator? So this is no, it's yeah, correct, 0.5 to 0.5 and then no, is it correct? 3.5 to 5, what is the again 0.5? You are not getting more than one, right? You will not, we should not get, okay. Yeah, 0.5 into, what is this guy? $80,000, good. Plus 0.5 into 30,000, huh? Point, just 30,000, okay. Is it too bad or 0.5? Just 0.5, huh? No, this 30,000 is correct?
Into 0.5.
Into 0.5, right?
Into 0.5.
Vikram, is it okay? No, you are not convinced. No, 30,000 is area under the curve, but you should multiply it by the absorptivity, right? 0.5. Yeah, now you got 55,000 divided by 140, yeah? What is the answer? Yeah. Vikram, suppose we didn't had we not had this, is it correct English? I don't know. Suppose we were not to have this. Then after all this I will get 40,000 plus 30,000 divided by 140,000 is 0.5. What a silly answer, because we started with 0.5. Okay, alpha equal to 0.39. Now what should be the reflectivity of this surface? No, What should be the reflectivity of this surface? 0.61. The hemispherical total reflectivity of the surface will be 0.61. Everybody is clear with this? Now we have to go to, so part A is over, A part is over, B part, we just have 45 seconds. Yeah, you have to use the F function chart. I think I will stop here. Please use the F function chart, and what is the emissivity you are getting? 0.49. So it has got a emissivity is about 0.5, absorptivity is 0.39, okay, and then you have to have the net radiation flux. What is it? Plus or minus? It is losing heat. So it is emitting faster than. So we will work out all these numbers in the next class. So now you have a good idea of if there is a single surface, how to handle, okay. Like that there may be many surfaces, each may be having its own crazy behavior. Then you have to integrate and with respect to angle and lambda, and then put all these fellows together. Eventually the radiation problem will become a problem of solution of linear equations, because there may be many surfaces, you have to invert the matrix or Gauss-Seidel method or something. But what is the engine which is driving all this? Sigma t to the power of 4, spectral emissivity, spectral absorptivity and all. This is the basis for the whole thing. Eventually what you get as equation, they have to flow, the information has to flow from this, okay. So we will stop here.